Is the mic live? Yes, the mic is live. My entrance is your first lesson from this presentation. About 4 weeks ago, Louisa wrote to me to say, could you name a tune for a playlist for the party? So I named a tune. And then I realised that the tune you had named was the tune you were brought into. So I changed the tune. First, you read the manuals, then you observe what really happens. Okay, so this presentation is just Don't Do It. It's really a collection of things that people have done badly, ideas about how there are things you should avoid, things that you can do more efficiently, how you might approach problems of performance in various slightly different ways. Some of these things you'll notice immediately what the mistake is, the obvious sort of thing that's going wrong. Some of them you might have to sit back and think a little bit to say, well, how would I do that differently? How could I do that differently? Now, I've got an exciting new pointer here, so it'll probably break. Quick history of me. I'm a freelance independent. I've been working for a very long time with Oracle, but I have never worked for Oracle. A few little awards on the left there, the few books I've written on the bottom, and the few I've contributed to on the top there. So that's my life. Actually, that's slightly more than half my entire life with Oracle and IT. Okay, so let's get on with the interesting stuff. What do you try to do to improve performance? Answer, you try to spend less time doing the job. So how do you spend less time? Well, one, don't do it. I was actually on one site 4 or 5 years ago, and they asked me to look at a particular SQL statement, and it was a statement that ran every 15 minutes. And it took 14 and a half minutes to complete. And this was not good. So I had a quick look at the text before actually trying very hard, and said, what's it actually trying to do? And they said, well, it's a report which tells us which products are getting very low in shelf life that we ought to be reordering. So I said, well, how often do you reorder? Once at the end of the day. Well, why are you running a report every 15 minutes that tells you what to do once at the end of the day? Why not just run it once at the end of the day? Oh, that's a good idea. Don't do it. Right? Complete waste of effort. Actually, I think in the end they ran it twice, so get some sort of prediction of probably what was going to become by the end of the day, and then much closer to the end of the day what they really needed to do. And of course, in a way, it's not don't do it in their case, it was just do it less often. But when we talk about do it less often, it's more focused on things like, there's this query which is running 3 million times per hour. That cannot be run by human beings. That must be run by a program that's doing something remarkably stupid. So things that happen extremely frequently are basically very dangerous. They cause lots of contention. So don't do it less often, or just do it more efficiently. And most of what I'm going to talk about is doing it more efficiently. but that's not exclusively what I'm going to talk about. Here's an example that came from OTN, and someone coming up with, I've got this query, it takes 28 seconds to complete, how can I make it go faster? Okay, here's the execution plan for that particular query. Now, if you look at it, you can see here that basically we're picking up 8 million rows and 250 megabytes of data. We're selecting that, we're doing a group by. We don't really trust the numbers that come out from the aggregation because Oracle does some funny arithmetic, but to pick up and handle 8 million rows and quarter of a gigabyte, and maybe that's extracted from a much bigger table, in 28 seconds doesn't really look too bad to me. That's a starting thought. It's an awful lot of data. Okay, so what can we say about this? Well, one person suggested, let's create a covering index. Let's create an index that covers every single column in that particular query. And the person actually tried this, and the query ran 8 seconds faster. Okay, of course, it was doing an index fast full scan to do that, and possibly if it had been forced into a full scan, the sort group by, which is here, whoops, I told you something would go wrong. The sort group by, which is here, might disappear, and maybe the sorting is part of the problem. But actually, it's quite difficult to get rid of sort group bys if you're dealing with partition tables. Running the query in parallel would make it go faster, probably. But at 28 seconds, maybe not very much. So what do? Find out where the time is going. That's always the first step. Now there's all sorts of ways you could do it, but hey, the query only takes 28 seconds to run. So let's just run it again and see what happens in the next 28 seconds. But before we do, let's just switch on auto trace. Set auto trace on statistics so I don't get the output. And this is what we see, and I've highlighted a couple of the figures from there. We are processing 1.6 million rows, and we're doing 100,000 SQLnet round trips. Well, that's SQL Plus picking up 15 rows at a time, 100,000 times. Where do you think most of the time is going? It's on the network. So, having told the person to do this thing with auto trace, I said, okay, now try this. Do it again, but set array size 1,000. It's now going fast enough, was the response we got. Yeah, it was probably going about twice as fast. That probably clicked off 16 seconds without the index in place. He actually came back and said, with that index and that index fast full scan, we dropped to 4 seconds. Right? It would have been a bit slower for the table scan, and frankly, I think putting the index on was a bad idea because it's a very expensive thing to do just to trim a few extra seconds off. So, array processing, large volumes of data, array size. Do the round trip less often. And of course, it depends on your technology how you do that. I have to throw in here something which says if you're on JDBC, there's a row prefetch thing which you can set on the connection to ensure that you're not doing very large numbers of round trips. So easy, cut down the number of times you're doing it. Updates, superfluous updates. This happened quite a long time ago. I got called into a client, and amongst other things, I had a problem because the SLA for the overnight batch was 2 hours, and the overnight batch was taking 2.5 hours. So one very simple thing to do was just to run up a couple of AWR reports or StatSpec reports and say, well, can I see anything really expensive and really slow, and see if I can make it really quick by comparison. And this was something that came out. There's an update statement here, and this update statement is terribly simple. Update the history, set the state to 0 where the flag equals X. It's done 2.9 million block reads in one execution. It's taken over 20 minutes. I'm only looking to knock 30 minutes off the time it takes to run the batch job. Great, that's 20 of them. I'm sure I can do better. Well, I hope I can. History. We change everything to 0 where the flag is X in history. Quick check of what's in the history table. Oh, several million rows. All of them, except a few, have a flag equal to X. All of them, except a few, have a value 0. So what happens tomorrow night? A couple of hundred rows appear where the state is X and the value is not 0. We get a couple of hundred rows which need to be updated. What do? We update 5 million rows. How do we not do what we don't need to do? We just change the predicate, where the state is not 0. We update 200 rows instead of 5 million. We cut down a huge volume, literally hundreds of megabytes of redo. The thing ran twice as fast. Well, okay, that's only 10 minutes saved. Whoops, there we are. That's only 10 minutes saved out of the 30 I'm trying to save, but you know, it's a good start for doing virtually nothing whatsoever. You do have to be a bit careful, by the way, when you're doing this, as it notes down there. I might have needed and state or state is null in order to do the correct update, but in this particular case, state was declared as not null. So that's a massive improvement, but we're still doing this 2.9 million block table scan in order to update 200 rows out of about 5 million. What does this suggest to the alert reader? In one word? Surely someone said index. I'm sure I heard someone say index. I'm sure at least half of you shouted out index. But my hearing's not very good these days. Okay, so we create an index. What's bad about indexes? They tend to be big and expensive to maintain, and something else might use the index that you've just created in a very, very bad way. How to avoid that happening? You create a very, very specialized function-based index, which is extremely small, highly unlikely to be used by any other process. So we'll create this index. We create an index on, can I do it like this? Yes, I can, maybe. We create an index on a case statement. Case, when the flag equals x and the state is not equal to 0, then return a 1. We create an index where the only entries are exactly the entries that we want to update. It's an index with about 200 entries at the best, and as we update the rows, they disappear from the index and the index vanishes to nothing. It's something like a one block only index. It's the tiniest possible index, and it's such a bizarre function in that index that nothing else is likely to want to use that index. Now, when we create that index, we'll be creating a virtual column that's hidden away underneath the index. That's the traditional implementation of a function-based index. If you need to find out what the name of that column is, we can check user in columns. If we create a function-based index, you have to gather stats on that hidden column. Now, the next time you gather stats, that's okay. This column will get the stats. If you create the index, the next step you should do is to gather stats, either on the column explicitly, or perhaps with something as simple as saying this: gather stats for all hidden columns. Right? The hidden column, by the way, will have a name like this: sys_nc something 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 number $. With this in place, the whole update takes fractions of a second. Nice little detail, by the way, about this particular update. The couple of hundred rows I'm interested in all arrived last night. So they're all physically close to each other in the same table. We get a very good caching benefit. We're not having to read 200 different blocks scattered across the entire width of the table. It's incredibly efficient. It goes incredibly quickly. I saved 21 minutes. I've only got 9 more minutes to go. And the next statement I'm going to look at actually took 40 minutes. It's just that it was going to be a bit harder to fix. So, customer was pretty happy with that. I made a safe, very good improvement on their performance. Okay, what's next on the list here? Oh, yes, a little bit more about this particular thing here. I've got here my select statement. That's the select statement which would pick the rows I want. Just to demonstrate, my execution plan says I can now do an index range scan, and when I check my index access predicate, there's my access predicate to an index. It's saying, yes, this is exactly the predicate which you used to create the index in the first place. 11G, rather than creating this function-based index or this funny expression in the index definition, you might create a virtual column and create an index on the virtual column. There's a slight threat to doing that, of course, because someone somewhere might have done a select star from table or update table without specifying a set of columns, set load of columns equal to x, y, z, done something crazy which means the code breaks because there's an extra column there. In Oracle 12, we bypass that problem because Oracle 12 says when you add your virtual column, if you want, you can add it as an invisible column. So it won't accidentally break any of the other statements in your system. Okay, subqueries. Subqueries in the select list can be extremely useful, particularly, for example, when you do I've selected a couple of thousand rows from a table, now I want a slightly complicated expression, which perhaps was an aggregate expression, as a selected column. Well, maybe if I put that as a scalar subquery in the select list, first off, it will avoid me growing a huge amount of data and then aggregating it down through the normal join mechanism. Secondly, it may be that with scalar subquery caching, Oracle can remember what's happened in previous executions of that particular scalar subquery and not have to run the scalar subquery for every single row. So it can be very, very effective. But someone on OTN said, well, I've got this query which is running too slowly, can you help me? This query is actually querying, as you can see here, a table APO, geo-APO. It's got 15 million rows in it. Hang on, why are we doing 15 million rows? Oh, it's a group by, that's okay. Right, the answer's going to be very small. Right, 15 million rows. What are we doing with those 15 million rows? Well, we're selecting count of ID and then a case expression. Case, when exists, subquery. Now notice this subquery, this subquery says, I'm going to a table called apps, I had geo-APO, I'm going to a table called geo-apps, I'm mapping by user ID, where the PO attribute 1 equals y. So the first option in the case statement is we run the subquery, get a y. But if we don't get a y, what do? We say, well, okay, next option, when exists, join to the same table, geo-apps, and check if PO attribute 2 is y. So we might succeed there. But if we don't, we'll do the same thing again to check if attribute 3 is y. And if it isn't, we'll check attribute 4, all the way through to attribute 20. So for every one of those 15 million rows, we might actually run 20 slight variations of the same subquery. Oh, and then, by the way, see the group by clause? What are we grouping by?
Same.
The same. For every row in this table, we may run the same subquery 40 times. At 15 million rows, that's 600 million executions of an SQL statement. And for some reason, this query is running too slowly. Right? Anything that runs a large number of times is almost guaranteedly a mistake. Okay? What are we really trying to do? Find out how many times we use PO attribute 1 first, how many times it's PO attribute 2 first, and so on down to PO attribute 20. If we're really lucky, we'll always find its attribute 1 and we'll only run that subquery 30 million times. If we're really unlucky, we'll run that subquery 40 times per row for 600 million executions. Right? I think we need to do a join. And of course it's very simple SQL. There's our, where are we? Our APO apps table from geo-APO, geo-apps, outer join to the apps table here. Our case statement simply says when attribute 1 is a y, then we'll have the word 1. When attribute 2 is a y, we'll have the word 2, and so on. And group by. Right? Job done. You still have a 15 million row table scan, but it's now an awful lot quicker. So do be careful with subqueries. Subqueries, scalar subqueries in the select list are not necessarily a good thing. Here's one I did for a, what do they call it, social network type thing. They had a problem. They described the problem to be like this. You become a member of this particular social network and you're allowed to produce a blog page. And you get friends with people, and your friends are allowed to view your blog page and vice versa. And to allow your circle of friends to grow, you can view the page if it belongs to a friend or a friend of a friend. Again, of course, the way various bits of program work and caching works. There's a friendship table, which says if you're my friend, I'm your friend, and that's a unique relationship. So we've got a table with that as the primary key. When I insert you and me, a trigger fires which inserts us the other way around. Friendship works both ways. And of course we have both IDs available when we do this check. And their problem was this check of, am I allowed to see your blog page, was taking too long. And it was very simple code, a very obvious code. Here's a bit of SQL which says, I've got two values there. There's my ID and your ID. Select counter star from the friends table, where my ID equals bind 1 and your ID equals bind 2. If that count is 1, I can see the blog. If it's 0, you're not a friend. So let's do this check friends of friends. How do we check friends of friends? That's my ID. fr1.myid. We'll join to friends again, saying my ID, that's the first friend there. That's all my friends in turn, and is at the opposite of that join. Do you appear? Are you a friend of a friend? And this code was just taking too long. So they thought, well, we don't really need to call in an expert just yet. All we have to do is remember that you should only use one SQL statement if you possibly can. Don't use PL SQL or words to that effect. So they said, let's change the code, let's do this. That's the bit which finds out if you're my friend. That's the bit which finds out if you're a friend of a friend. We'll make it one SQL statement, union all, select count. So their code now runs more slowly. If the count is non-zero, you view the page. If it's 0, you don't view the page. But it runs more slowly because now you always do that bit, but whether or not this actually found a row, you always do this bit as well. Whereas previously, with a little bit of SPL SQL, you could stop early. So they called me in and said, how do we make this go faster? And I looked at it and said, well, your SQL cannot go faster. It is doing the least possible work your SQL can do. But you could try changing your English. How do we phrase the question? I can view the blog if you are a friend of a friend. Let me put that another way. You can view the blog if we have a friend in common. Everyone happy with the English language translation? That's my friends, that's your friends, that's the friends we have in common. And just to keep the code looking the way it was and make the minimum change, that's if you're my friend, union all, select count star. This ran literally 2 orders of magnitude faster than their previous code. And I did not optimize their code, I optimized their English. Step away from the problem, explain the problem to yourself, explain it in a different way, and maybe a different explanation gives you a different SQL interpretation. Why was it 2 orders of magnitude faster? This was a social network which principally catered for teenage girls, each of which typically had 200 friends. That's me and my friends. For each of my friends, I look at all their friends. The number of routes I go through and count is n times n. 200 times 200 is 40,000. Intersect, 200 plus 200 is 400. That is 2 orders of magnitude less work. Multiplication is dangerous. Which is why sometimes a nested loop is extremely dangerous. Because a nested loop cost and a nested loop number of buffer visits is a multiplication job. And sometimes the optimizer picks the nested loop when it shouldn't do, or uses the wrong numbers in the multiplication. Okay, there was actually a quicker way. I didn't think of it at the time, but I thought of it the next day. Having actually written this little piece of code, I could have actually done the short circuit bit and said, well, if we do a select counter star from dual where exists, an existence subquery says I will stop on the first success. So if I'd written it like this, if you were a friend, existence would be satisfied here, and this bit wouldn't even run. Right? But I didn't think of that till the next day, and I'd already written out the bill. So I waited for them to come back a couple of months later to ask me for a better way of improving it. They never did. They didn't need to. Okay, so change the problem, change the question. You know the thing I said, shouldn't do it in PL/SQL, make it one SQL statement? Too many times people on the internet, OTN particularly, say never do in PL/SQL, that which can be done in SQL, which is a remarkably stupid exaggeration. Someone came up with this on OTN. They said, I've got this piece of code, how can I make it faster? And immediately got hit by someone coming back with this, don't do it in PL/SQL. But why would you do this in PL/SQL? I want you to think about this, because there's a very good reason. Okay, so we declare a cursor there, select star from T1. We're declaring the type for that cursor and an array to hold rows from that cursor. We're going to do a begin, open the cursor, run a loop, close the cursor. In that loop, we're going to say bulk collect, fetch 255 rows at a time, for all insert, bulk insert, save exceptions. And we have an exception handler here. Now it's only framework code, so this exception handler would be the exception number, which we could set up with a name to say, when we have a bulk exception, we're going to do something. Now, why would that be a good idea? Instead of simply saying, insert into T1, select star from T2. Think about that for a moment, because there is a very, very, very good reason. And everyone who responded to this question said, you shouldn't be using PL/SQL. I'm sorry?
Exception handling.
What? Exception handling. Exception handling. Yeah, I mean, I put it in dark letters so you can see it really easily. I'm not jumping off there again. Certainly not trying. Isn't that what Darth Vader does? Certainly not going to try and climb back up. It was a lot further than I thought it was when I looked down. Yeah, exception handling. What happens if your massive insert goes wrong? You roll the whole thing back. What happens if you get the odd error here? You pick out the one row that's caused the error, everything else goes in, you've got a way of handling the error. So it would be quicker to do an insert as select, provided you guarantee that nothing ever goes wrong. So if you drew a picture, time going across the page, okay, here's our pure SQL, might actually be about twice as fast as that bulk collect. Might be, if everything goes perfectly. What happens when the pure SQL gets an error and rolls back? Rolling back is slower and much more expensive than doing the insert. Oh, that's okay, we'll just validate the data before we insert it to make sure it's okay. Oh yeah? How long does it take to validate the data? Right? It's going to take longer to validate the data one row at a time, or however many validation tests you've got to do before you get a pure fast insert. Which is the best strategy? But if you're expecting a tiny amount of erroneous data just occasionally, that sounds like a really good argument for saying it'll always take 6 minutes rather than mostly taking 3 minutes and occasionally taking an hour and a half. Never say never. Sorry, you're supposed to chuckle at that one. A little laugh? Never say never? Oh, well, never mind. Okay, this was a nice one. This was a really interesting little problem here. I have to describe it a little bit. It was a client, right? They had a large data table. In fact, it was only 500,000 rows. They had a big table which had 8 attribute columns in it, which were all declared not null. So there were 8 attributes, okay? All of them not null. There was a types table which had the same 8 attribute columns, but the rule was at least one of them has to be not null, but 7 others could be null. No idea exactly what you might have there. There were only about 900 rows in that table. Now the thing was this, for each row in the big table, you had to find the row in the little table which was the best possible match on the available attributes. Right? So that was the task. For each row in the big table, find the best possible match. Well, what does that mean you have to do? For each row here, 500,000, you have to examine 900 rows to figure out which is the best match. How many checks are you actually going to do? 500,000 times 900, 450 million. You're going to generate an intermediate result set of 450 million rows, and then throw away 449,500 of them. Oh, got that wrong. Nearly all of them. Easy to write the code. Big table joins a little table, and down here, join attribute 1 to attribute 1 from the types table to the big table. But if that's a null, stick in the attribute 1. That's the join. And then when you've joined all that data, you walk through it and decide which is the best possible match. That's what you have to do. In fact, typically, one of the rows in big table would actually be suitably similar to 2 rows on average in a little table. And there were extra columns on the little table which said which is the more preferable of those 2 rows. Let me show you just a little example of the data to try and highlight how this works. Here's 2 rows from my big table, okay? And here's 3 rows from my types table. So if we take the first row from the big table up here, 1, 1, 2, 1, okay, that's, I've got 4 attributes there, and compare it with the little table, 1, blank, 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 okay? Nothing contradicts, so that's a match. We'll go the 1, 1, 1, 1, 1, 1, 2, 1 against the second row here, 1, blank, blank, 1, nothing breaks there, so that's a possible match as well. And the last one, 1, blank, 1, that disagrees with the 2, so this doesn't qualify, so that's straight out. So the first row in big table would say here are 2 possible matches, and then this attribute here actually allows you to pick the most appropriate if you've got more than one match. You can run through the same procedure to find that these 2 rows from the small table, the types table, match the second row in the big table. You have to compare every row with every row, right? Except you don't. Because I asked the question, if we looked at the big table, how many distinct combinations have we got of attributes? And the answer was 400. Well, that means we only really need to do the comparison, the difficult bit, 400 times, not 500,000 times. So we'll do the comparison 400 times, and then say, well, for each of these 400 that we've got, we can now just do a straight equality back to the big table and say, this pattern, yep, you're a row that's on this pattern, so you get this particular match. In other words, we work through the big table twice, because it's quicker to work through it twice than it is to work through it once. Subquery factoring here, just to make it easy. With distinct data, select the distinct attribute sets from big table. It's 400 rows. Okay? We'll join this distinct list to the types table. And after we've done that join, we'll go on to the big table. How do we join the distinct types to the type table? That's when we do this really nasty thing here, which is the sort of NVLing of the outer joins and all the rest of it. This is the brute force, vicious, nasty little Cartesian join. But it's 400 times 900, which is 360,000, not 450 million. What we get from here is about 400 plus a few extra, call it 500 rows, where we've got exactly this combination of attributes goes with a specific 1 or 2 type rows. So we can then say, okay, let's now join what's survived. The big table joins to what's survived when we did this really huge, messy Cartesian join. It got the right answer. At first, they didn't believe it had got the right answer because I put in all the extra processing which says, oh, by the way, since it's so quick, we might as well throw away the stuff we don't want at the same time. So I actually got the right answer and they got the wrong answer. And so I told them which bits of my code to eliminate to get the wrong answer. somewhere between 20 and 30 seconds instead of 2 hours. And this was a good thing, because one of the other countries they were running this query from had 2 million items to start with, and they had never ever finished the query within the entire overnight SLA. 20 seconds, because I rethought the problem and examined what the important bit of the data looked like, and because I could do something 400 times instead of 500,000 times. So what we've got, this was the execution plan at the end of it. There's my loaders select. That's picked out my 400 rows that are matter, 400 distinct patterns from big table. Down here is where I say, well, just do, it says nested loops outer, it's lying a little bit, it's actually a Cartesian merge join because everything has to be compared with everything. That is predicted to return about 500 rows, it's fairly close, and then we do a hash join between that and the big table on the 4 known exact values of the attribute types. 20 seconds instead of about 2 hours. It's written up on my blog if you want to look at it. This, of course, is an example of what oh, no, I'm not going to pop up that thing just yet. Next, similar sort of idea, the intermediates table. This is another one of these things where people get sort of apoplectic with rage if you suggest it. They burst out with, Oracle doesn't need temporary tables. Well, there's materialized views in subquery factoring, there's non-mergeable views, there's 4 or 5 different ways in which Oracle uses temporary tables. So what's this about Oracle doesn't need temporary tables? Just because you hate SQL Server? Of course you have temporary tables in Oracle. Occasionally. You generally don't need them. So here's this thing. This statement takes 7 hours to run. Probably need to trim a bit off that one. This statement takes 7 hours to run. How do I reduce the runtime? Okay, the statement, let's look at the from clause first and the tables. If you don't recognize the significance of this table here, MSISDNs, it's telephones, mobile phones, okay? You always get big problem statements from phone companies. All we're doing here, we've got 2 tables which really matter here, the number ranges table and the MSISDNs table. Let's bring in what we're looking at. It's the count the number of MSISDNs, and what we've looked at is here's a number range count of the MSISDNs. And when we check the where clause, all we're trying to say is, I've got a row which has a start number and an end number. How many of my available phone numbers currently fit in that range? Right? We're starting with 10, ooh, that's exciting. We're starting with 10,000 rows here in my number ranges, 72 million rows in my MSISDNs, okay? Here's our predicate. The important bit of our predicate, well, that's trivial. The available phones, the numbers available, the phone numbers which are between the from number and the to number. Now, what's the problem here? For each number range, you have to examine 72 million rows in order to determine which of those rows is available and falls between those 2 numbers. Well, I only had to worry about 450 billion rows in my last query, right? This one has got 72 million times 10,000, which is 720 billion. No, 720, a very big number. It's huge. We have to do it this way, basically. This is a problem. You cannot bypass, in general, this particular issue. For each row here, we have to examine every one of those 72 million in order to decide if it fits the gap. We're going to get an absolutely huge number in our join. What have we got? Down the bottom here, we've got our MSISDNs. Oracle, this was the plan I think that came from the end user. Oracle's estimated there will be 13 million. Wow, that's a relief. It's only a quarter of them. It's probably a bad estimate. And we've got here, this is actually 3 other tables being joined, but the number range is the significant thing. That's 2,200 number ranges Oracle thinks are going to come out of those joins of the other 3 tables. But what are we going to do? We're going to sort this lot here. We've got to sort up the top there. We're going to do a Cartesian merge join, not a Cartesian. We're going to do a sort merge join between those 2 sets. Oracle thinks it's going to be 2.4 billion rows in the result set. And it's not all that far wrong. It is literally billions. Okay? This is what I call the Brontosaurus query. Now, those of you who like dinosaurs will recognize that this is now called an Apatosaurus, but I call it the Brontosaurus query from a Monty Python sketch. Right? If you know the sketch, you'll know that the Brontosaurus theory says a Brontosaurus is small at one end, small at the other end, and big in the middle. Right? The Brontosaurus query starts with a small number of rows, number of ranges. It ends with a small number of rows, the ranges with the count of how many phones are in that range. But in the middle, it produces a huge volume. Doesn't store it, throws most of it away, but it's huge. And when you spot the Brontosaurus, you have to sit there and say, can I avoid the Brontosaurus? How do I cut out the bit in the middle? Right? And sometimes the answer is you create an intermediate result set. This query takes 7 hours to complete. By the time you get the report, it's 7 hours out of date. So what could you do? Right? You've got to get rid of that big bit. Why is it a big bit? Because you have to examine every phone number. So let's find a way of not examining the phone numbers. Now, in 12C, there's a terrific method you can use, and I'll come back to that in a moment. Before 12C, why don't you create a result set which says, let's create a table which has got all these phone numbers in. We'll sort them in order as we create them and number them. We'll give them a row number so that the row number matches the correct sorting order of these tables. Then if someone says, how many phone numbers are there between X and Y? We can say, well, X is row number 1003, Y is row 1096. That means there are 94 rows, because we can just say subtract that number from that number. And we don't look at all the stuff in the middle. Sort them in order, give them a number in order, and suddenly you don't need to count them. Just find the start, find the end, find the difference. Create a temporary table. Right? So we'll create a temporary table. There's all sorts of ways in which you might do that. Simple insert append into, I've said MSISDN row number over order by MSISDN. That gets me the right number on each row in that table. I ran up a little test with 40 million rows in it. It took me 2 minutes to build this table, including the index. You might have done it into a global temporary table, hence my GTT. Okay, once I've done that, what can I do with my particular data set? I just write a query which takes advantage of that unique index. I take my number ranges, I take my set of MSISDNs twice. Another time I've used the data twice because it's quicker than using it once. This is what I'm going to join. What am I going to do in my join? I'm going to say the from table, one of my MSISDNs, I've called the from table. From one is select the minimum value from the table. Have I got this right? GF. Yes, the from table is the minimum value from these MSISDNs where the value is greater than or equal to the from number in the range. The to join goes to the maximum number from the MSISDNs, where the MSISDN is less than or equal to the to range. That just picks up start point and end point for each number range. And all I need to do then is produce this expression, which simply says, I had a counter for the to table, I had a counter for the from table, subtract and add 1. Answer. Job done. 0.02 seconds. Right. Execution plan, conveniently I knew Oracle could do this. We do a full table scan of our number ranges. For each number range we go into the from table, but there's this wonderful first row's min-max range scan optimization which just says 3 buffer visits and I hit the right row. And then we do the same nested loop join into the to table, 3 buffer visits, I hit the row I want. Average 7 buffer visits per number range, 0.02 seconds. Job done. 2 minutes to build, forget the whatever fractions of a second. What's wrong? Apart from the answer.
Consistency?
My list of numbers is not consistent. with my list of ranges. I'm using numbers which I generated 2 minutes before I ran the query. So I have got a result which is not a self-consistent result. Hey, but it's only wrong by 2 minutes. The last time I gave you the result, it was already wrong by 7 hours. Right? Now, what do you want? The right result that would have been right 7 hours ago, or the wrong result which is only out by a tiny bit? Sometimes you deliberately choose to supply the wrong answer because the wrong answer is good enough and fast enough. Oh, and by the way, I can fix that. Right? Because when I populate my table, I can say, get the current SCN, insert into this table of MSISDNs as of this SCN, and then once I've got that data in place, I can say to Oracle, run this query which says, select from the number ranges as of that same SCN joined to the current contents of that MSISDN table. And I get the right answer. I get a self-consistent answer as of 2 minutes ago. Brilliant, isn't it? Okay, now I thought I was absolutely fantastic when I first did this as a presentation. There was a guy in the audience called Stu Ashton who came up and said, do you realise in 12C you can just write an SQL statement and forget about all this intermediate stuff? And this is a very important point. Brendan Tierney was talking about analytic functions yesterday. Jim, whose Polish name I can't pronounce, Trapinski? Absolutely correct, that man, thank you. Was talking about analytic views 12C. Analytics, there are loads of functions built into Oracle, which means you don't have to select 1.6 million rows from a table and pass them to the front end for the front end to crunch it down into a couple of hundred. There are loads of analytic bits, and in 12C there's the match recognize thing. Now, Stu immediately came back with this answer which said, well, if we assume the number ranges don't overlap, well actually, if they don't overlap, I could have done it with an Oracle 8 analytic function. If we assume the rows don't overlap, here's a very simple solution, okay? We'll select the from number and the to number from the number ranges, union all, select all the numbers and null from the MSISDNs. We will then introduce match recognize, and match recognize comes in, select star from the match recognize result. Right? The first bit, the union all, produces some data which will be manipulated. We select from the match recognize result. We need an or do I clause, from number to number. We need to define some patterns. There are A-type rows and B-type rows. An A-type row is where the to number is not null. A B-type row is where the from number is less than the previous to number. Right? A pattern consists of one of these followed by 0 or more of those. And what we're going to report is the from number, the to number, and rather than reporting every row, we're going to count those rows. I think someone's just given me a hint I've got it on my time. Shall I go on?
Yes.
Correct answer. Okay, so that's our match recognized. Really compact code. To make it easier, let me just show you a little set of data. There's my number range, just two of them. 3, 6 is a number range, 8, 13 is a number range. Here's some numbers. It's going to be the odd numbers between 1 and 19. Okay? Those are my two tables. The driving part of my query, the match recognize, basically says do a union all between them and sort by the from number and the to number. Now, because of the nulls that are in the number ranges, this is what the data looks like. Okay? You can see very clearly I've got the 1, 2, 3, 5, 7, 9 all the way down to 19 here, but my number ranges pop in here. The number 3 there with a to number from the number range appears just above the 3 null. Okay, here I didn't have an 8 at all. The next number up was a 9, but 8, 13 has appeared just above the 9s. So what does match recognize do? It says an A row is a row where I've got both columns filled in. So my first A row is here. So Oracle says, okay, let's find the first A row. I want an A followed by 0 or many Bs. There's my first A row. Now I just walk down the list saying, well, what goes with that A row? My B rows say any row where the from number is less than or equal to the to number up ahead. So everything less than 6. Found the pattern, reported. Keep on going down, there's another A row, which rows following it match, those 3. There's a pattern, keep that, report it, carry on down the list. We spot patterns. And then my rule for reporting was just show me the A, the B, the from number, the to number, and the count. So I end up with this. And Stu Ashton said, I ran up 40 million numbers just like you did, and it was quicker than your version, but not by much. It's brilliant. I had to do something really quite devious and clever and cunning and thoughtful. But if you know this type of stuff appears, and you can look at your problem and say, we're looking for a pattern, match recognize might be the thing you do. Essentially, you sort the data and you walk through it. Now, of course, historically, you might have, well, I'll sort the data, I'll pull it through a PL SQL cursor, I'll use PL SQL to walk through it. That might be a really smart move. A rather less smart move is, I'll run the SQL statement, I'll pass the entire 72 million rows up to the front end to SAS or whatever, or Java or something, and let the Java work out how to compress it down to 1,000. All of that type of processing gets pushed into the database where the minimum amount of effort can be spent doing exactly the same sort of processing at machine code speeds. Before you do any difficult coding, go to the manuals on analytic functions if you're on 11G or earlier, or match recognize if you're on 12C, and see if you can actually just write what is effectively a simple SQL statement that does the job in exactly the intuitive way you would think, but does it in the SQL. So that's match recognize. As I say, with the introduction of the assume the numbers don't overlap, I could have written something which isn't quite this efficient, but is in the same ballpark, even as early as 8.1.6. Okay? Here's the execution plan, by the way. Key feature, what we've got here, match, recognize, sort, deterministic, finite auto. Deterministic, finite auto, by the way, is quite comforting. It means it's just a sweep through the data once, not go rocketing back up and down like crazy forever. Sort. The major cost of this tends to be the big sort, which gets the data in the right order so that you can walk through it. Right? This just did a million row sort on the little example which I ran up. So I now can come to my final slide, okay, which basically says, one, think technology. What are you actually using? You're using a very sophisticated piece of software which can do more than just select a list of columns from a table. Think technology. Array processing is a good thing. It cuts down lots of repetitions, lots of starts and stops, lots of contention. Updates. Look for redundant updates. People often do it wrong. Don't update stuff that doesn't change if you can possibly avoid it. Scalar subqueries, brilliant mechanism, but only when used in the right place. Do not allow a scalar subquery to execute a very large number of times. Check the requirement. Can you state it differently and come up with a different coding strategy for it? Because maybe it's the problem that needs to change, not the code that needs to change. I've emphasized this one. Using a table twice could help. It's counterintuitive, but let's do one pass that gets some data, fiddle around with that, go back to get the rest that we actually need. I've got several items on my my blog which are different ways of presenting problems solved by that approach. Temporary tables, this isn't necessarily Oracle Global Temporary Tables, it's scratch results. Sometimes are the best possible thing that you could do. They are not always a bad thing, but quite possibly it might be, do you want a nearly right answer now, or do you want the right answer tomorrow when it's 24 hours out of date? Right, the time it takes you to get it and the potential correctness, that's big data for you, by the way. What's the biggest difference between relational databases and big data? You get the wrong answer with big data, but it's quick and it's close. Close enough. Relational is about getting exactly the right answer with no risk of error, right? But you don't always need that. That's why big data works. Because the nearly right answer, the good enough answer fast enough, is often more important than it was a perfect answer, but God, I'd have done better with it yesterday. Okay, and I'll finish off, think new technology. And at that point, I'll say thank you very much.